Good afternoon. Okay, today we will continue our discussion about calculating rotational inertia I. So we have listed all different kind of a rotational inertia for different shapes, but you can notice that all of those are relative to the center of the mass of those objects. So a ring, a disk, or a hollow sphere, solid sphere, a rod about the center, all of these are assuming that they are rotating relative to their center of mass, right? So if you have a ring, this is assuming you're rotating relative to an axis going through the center of the mass of the ring. But not all the time. Sometimes you have a axis somewhere else. So how do you calculate the rotational inertia if your axis is somewhere else? So we're going to use a parallel axis theorem. This is saying that, well, if you know the rotational inertia through the center of mass, and if the new axis is at a distance away from the center of mass axis, then you simply add md squared to the center of mass rotational inertia, you get the new one. Now, for example, again, if you have a ring, you know that I through the center of the mass for the ring is mr squared. But instead of rotating relative to this axis, you're letting rotate relative to this new axis, right? And the distance between them is d, which is also r in this case. So I relative to this new axis, if you call this p, will be ICM plus md squared, which is mr squared plus mr squared. So it's 2mr squared, okay? So you can see that through the center of the mass will always be the smallest rotational inertia, indicating it's always the most easy to rotate something relative to its own center of mass, okay? All right, so let's look at a quick clicker question. So if I give you a rod, one is through the axis C, through the middle. This is a uniform rod, it's uniform density, and or you can rotate it relative to one end, given by choice E. So through the end or through the center. So how do the moment, rotational inertia or moment of inertia compare between these two cases? So I'm going to go ahead and let you vote on this, okay? All right, so let's run the clock for 10 more seconds. 10 more seconds. Okay, any last minute vote? All right, I'm gonna go ahead and close this. Yes, you can see that the majority of the answer B is correct. Very good. We know that the rotational inertia through the center is always going to be the smallest, right? And if you put the axis to the end, it's going to be harder now to rotate this object. So IE is going to be larger than IC. And then you can also calculate exactly how much larger. Now, if you know the parallel axis theorem, you could have done the integration like what we did in the previous class, right? We did the integration from negative d over 2 to d over 2. We calculated this to be 1 over 12 ml squared. Or if we do from 0 to d, to integrate, we got this to be 1/3 ml squared. So this one is bigger. You could also argue, well, this one is through the center of the mass, and we know that is 1/12. Now this one is through another axis that is at a distance d/2 away. So you could use parallel axis theorem to calculate this distance. Center of the mass rotational inertia is 1/12 ml squared, and m plus the distance. So distance from this new axis to the center of the mass axis is L/2. So you plug in d is L/2, and this is 1/3 ml squared. So IE is bigger. Okay. Similarly, you have already done this question in your checkpoint online checkpoint questions. So you have a rod, and this rod is massless. You don't have to think about the rod, the mass of this rod. So really you just have to think about the 3m and the 1m. Okay, so we have this object. You can rotate this object relative to different choice of your axes. You can rotate relative to A or B or C, right? Each of them will give you a different center of the mass rotational inertia. It's asking which one is the smallest. So we know that through the center of the mass is always the smallest. If you only want to know which one is the smallest, all you need to do is find out where the center of the mass is, right? If one of the axes go through that center of mass, you know that the rotation inertia for is going to be the smallest. Or you can calculate each one of them and compare. If you do calculate each one of them, you can see that, okay, for relative to A, is going to be, because 3m is here right at the origin, right? So it's really just rotating m relative to the center of the origin is going to be m times L squared, the distance mL squared. Now IB, if you rotate relative to here, so this calculation is by viewing the system as 2 point masses. Because we already know how to do a point mass. Point mass, the center of rotational inertia for point mass is m r squared, right? Remember we derived this at the beginning of the discussion, is if you have a rope with a radius r attached to the center rod, and you have a little mass here, I is m r squared for a point mass, point particle, right? Now this is like 2 point particles. So you do one of them and add another one, right? So one of them, the 3m, is located at L/4 away from your rotational axis. The m is located at 3L/4 away. So this is 3L/4, 3/4. So you can add them together, you get, this is relative to axis B. You can also do the same thing for C, and you get the same as you get for A. Comparing all of these, you know that B is the smallest, right? So rotational inertia relative to B is the smallest. You could also calculate the center of the mass, where the location of the center of the mass is. So you still remember how to do the center of the mass. Is mass 1, location of 1, mass 2, location of 2, mass 1 plus mass 2, okay? Mass 1 is this 3m, okay? 3m is located at x equals 0. Mass 2 is m. Mass 2 is located at L. Mass 1 plus mass 2 is 3m plus 1m is 4m. So the center of the mass is at 1/4 L, 1/4 of L. So you know right here exactly where B is the center of the mass of the object, entire object. So of course, if you rotate it relative to the center, this is going to give you the smallest rotational inertia, right? So this one would be the smallest. So either way, okay, you can calculate the center of the mass and knowing this is smallest. If you calculate each one of them, you can rank them one by one. Okay. So now having the rotational inertia, we use this to look at rotational problems. A lot of times we look at the using the energy. So if they're rotating, they have rotational kinetic energy. If we have different objects, you have a solid sphere. The sphere is I is given. You have a ring. The I for ring is given. You have a cylinder. For a cylinder, we give a cylinder. It's like a disc. Okay, so this is like a cylinder. Okay, this is also given. They all have the same mass, same radius. Okay, and they are also rotating relative to its own center of the mass with angular velocity omega. So which one has the largest kinetic energy? So kinetic energy for rotation is 1/2 I omega squared, as opposed to kinetic energy for translational motion is 1/2 mv squared, right? We find the rotational counterpart by changing m to I, by changing v to omega, right? So this is translational, this is rotational. Okay. All right, so which one do you think has the largest kinetic energy? Okay, so I'm gonna go ahead and let you vote on this. Okay, so 10 more seconds. If you haven't voted already, please do so. Okay, any last minute vote? All right, if not, I'm gonna go ahead and end this. All right, very good. So you can see that if they're all rotating with the same rotational angular velocity, 1/2 I omega squared, if this is the same, is really whichever has the largest I is going to give you the largest kinetic energy, right? So, and they all have the same mass and radius, right? So it's really mr squared going to give you the biggest number. This one is 1/2, this 2/5. They're all smaller than the ring has, right? So the ring will have the biggest kinetic energy. Very good. So B is correct. Okay. So speaking of the ring, this is a checkpoint question you have already done. Let's take a look at this together. You can see that normally when we're talking about the mr squared, we are talking about this kind of rotation, right? Because only through this kind of rotation, so you kind of lay the ring flat, horizontal, and then you rotate it in the horizontal plane. Because this is giving you the I is mr squared. So all of masses have the same distance away from the center, right? So if you add all of the little masses, it's like the total mass times the same distance they have, mr squared. However, if you, in case two, if you're spinning this ring or the hoop, let it stand up perpendicular. And do we still have the same kinetic energy? Again, the omega is the same, right? So what we're really comparing is the I. Kinetic energy is 1/2 I omega squared. Omega is the same. So which one has a bigger rotational inertia? Case 1 or is it case 2? Case 1 larger than case 2 or smaller, or are they equal? So now this is the question, right? So if your ring is, you let it spinning perpendicular. So let me show you, maybe I'll take a ring and I'll show it to you. So case 1 is I take this ring and I rotate it like this, right? They all have the same distance away from the center. This is the center. But case 2 is having it stand up, and the axis is here, and this is rotating like this. So look at all the distance away from your rotational axis. Okay, so this point has 0 distance away. Here you have the largest distance away from your axis, which is r. Any point between here and here is in between 0 and r, smaller distance away from the center. So if I draw it here, let me draw it. This is your ring, this is your axis. This is r. So little mass here has a distance r away, but little mass here has a smaller distance. A little mass here has even smaller distance, right? Here they all have the smaller distance. This is r. And likewise, below, all of these little masses have a smaller distance. So when you do the adding them up, and if you are able to find a rotational inertia, you know that it's going to be smaller than mr squared. Mr squared is when all the masses are at a distance r away. Right now, it's really most of the masses is at a distance that's less than r, right? Only some of the masses is at capital R. If you rotate it perpendicularly like this, right? Only here and here is at r, but anywhere above or below is smaller than r. So you can see that, well, case 2 is actually easier to rotate a ring standing up because it has a smaller rotational inertia. I1 is larger than I2. So in which case that the spinning top have the most kinetic energy will be the case 1. Right? Okay. Any questions on how we compare the kinetic energy? And there's a question on would its inertia be similar to a sphere? It would still be different to a sphere, right? Because sphere, you have more masses all around the spherical surface. It's not just here on the ring, not just this hoop. So it's not going to be the same equation, right? Okay, so the problem so far we've been looking at has a stationary axis, meaning that it's simply just rotating in the same place. It's not rotating and moving at the same time. But we have a lot of problems. We have objects are moving and rotating at the same time, right? Like a yo-yo, like a bowling ball, like a boomerang. Or simply you can take a sphere and let it roll down a ramp. We will have a problem that we try to solve that way. You can take a hoop, you let it roll down a ramp. So it's rolling, right? It's spinning, and it's also going further. It's also translational. There's translational motion. So how do we look at those problems? The way we treat them is we will separate the translational motion and the rotational motion. We look at them separately. So we split this complicated motion into 2 parts. If something is only spinning, it's only just spinning in the place. Like think about a hoop, just spinning here. If something only moving, they're moving only in the translation mode. They're not spinning, they're moving like this. So when they're rolling without slipping, if they're rolling, meaning they're spinning and they're moving. So they're rolling like this as you go, right? So we're going to artificially look at this kind of motion and break it down into 2 parts. One part is the center of the mass of the object is simply just translating, just going forward. And the other parts, you can view the other parts are simply spinning spinning relative to the center of the mass, right? So we're going to break down the rotation in those two different parts. So your kinetic energy needs to be separated into two terms because not only you are spinning, you're also moving forward. The moving forward part is 1/2 mv squared, okay? That's the translational velocity. The spinning part, you're going to use 1/2 I omega squared. So combining those two together is the total kinetic energy of some objects that is rolling forward, which means they're spinning and moving at the same time. Right, so we're looking at this little diagram. The translational part is if you view these objects from far away, ignore that it's spinning. All you care is there's a dot, there's a point that is changing its position in space. That's translated forward. So of course, each of the objects will have a velocity moving forward, and we call that velocity the center of the mass velocity. Okay. Now, if you go and let's say you're standing on the rolling ball, this is a bowling ball. You don't really care that all the objects are moving, all parts are moving forward. You're only caring relative to my own center of the mass. I'm spinning, right? So each of the object you can see have a velocity sort of at particular points that relative tangential velocity looks like that. So you can add all of them together. If you trace one of the objects at different points at different times, at this particular moment, the total velocity is going forward this way. So this is the addition of the translational part and the rotational part. Okay. And to calculate the kinetic energy, you do 1/2 mv squared. V is the center of mass velocity plus 1/2 I rotational inertia times omega squared. Okay. This one is the rotational inertia relative to the center of the mass. Because the spinning part, we're looking at the spinning relative to its own center of the mass. So by doing this, there are quite a range of problems we can answer. For example, here I have a question. You have a block and a ball. So the block can only do a translational motion. It cannot spin, right? So the block simply just slide down the ramp. There's no friction. And the ball could spin. So the ball will roll down the ramp without slipping. Okay, so what I mean by no slipping is you just roll without like slipping backwards, right? It's just rolling without slipping. Which one has the most kinetic energy when they reach the bottom of the ramp? Okay, so it doesn't really tell you how fast they're rolling or translating or spinning at a particular moment. The information they're telling you that they all start from the same height. And that is very important. They start from the same height and you're looking at their kinetic energy at the bottom of the ramp. How do they compare, okay? All right, I'm going to let you discuss this within your group for a couple minutes. And when we come back, we can go ahead and vote. All right, so 10 more seconds to finish voting. Any last minute vote? Okay, all right, I'm gonna go ahead and close this. All right, so here is our results. Okay. We have a majority voted for the ball, and the next popular answer is they have the same kinetic energy. So how can we know what is the thing that they do share in common is the height. So how would the height come into play in terms of comparing their kinetic energy? How did you use that information? Anybody would like to share their thoughts with us?
I use the height to determine the potential energy of both the block and the ball.
Use the height to determine the potential energy. Very good. So they have mgh as their potential energy to begin with. Very good. Okay. And then what can we do with that potential energy? With that information?
We can set it equal to the kinetic energy.
We set it to the kinetic energy at the bottom of the ramp. All right. So we do that using the conservation of energy approach. Excellent. So we say whatever kinetic energy they have at the bottom comes from the potential energy at the top. Would that be a correct statement?
Yes.
Yes. So that's a conservation of energy approach saying energy final minus initial equals the energy input and output. Here we don't have any kinetic friction, so it's zero. So which means final energy has to equal to the initial energy, which is mgh. Okay, so they all have the same mgh to begin with. So they should have the same kinetic energy at the end. Now you wonder, I understand a lot of you voted for the ball because as the practice we did previously, if they are moving, if they are rotating, we have two different objects that are rotating with the same omega, right? The one that has a bigger inertia gives a bigger kinetic energy. Now you can see that they all have the same kinetic energy, but they may decide to use that kinetic energy differently. The block use all that kinetic energy to do translation, to move down. So you can see the block is simply, all that kinetic energy is just going to be mv squared because there's no spinning, they're just translational motion downward. The ball would be translating and rotating at the same time. So the ball will have the same kinetic energy, but as the ball going downward, it has the center of the mass of the ball moving downward, right? 1/2 mv squared. And at the same time, the ball is rotating them. So the part of that kinetic energy will go to rotation. Not all of it go to moving down. Part of that go to rotating. So that's 1/2 omega I omega squared. Okay, but those two are the same. They just divide it up differently. Okay, so with that in mind, I want you to go ahead and look at this particular question. You have already done it. Now we're going to watch a demo. We can have a race of different objects. Here, we picked a ring and a disk, or you can pick a ring and a sphere. Any two objects that you know distinctively, they have different rotational inertia, but they have the same mass. This is the same. They are built so they have the same mass and same radius. Okay, they're just made of different shape. Now you release both of them from the same height, and which one will win the race? Meaning that which one will reach the bottom first? Which one goes down first is the one that ran the race. So I'm going to go ahead and let you go ahead and predict, even if you may have already done this. Why don't you go ahead and predict and cast your vote? And then we can take a look at a demo, okay? Okay, you can see that they both have the same beginning potential energy. So they will, throughout the process, they're always going to have the same overall kinetic energy, but they may divide it up differently, right? Part of it is used to change the position of the object, and whichever ways you wanted to have a bigger center of the mass speed, center of mass velocity, because that describes how fast is changing your position from up and down. That is one that decide which one wins the race, right? All right, so any last minute vote? 5 more seconds. Okay, I'm gonna go ahead and close this, and I'll show you our results. Is pretty much quite evenly split between the three choices. B seems to have slightly more. That's the disk will win. So let's take a look at the actual experiment to see which one win the race, okay? Oops.
I'm going to demonstrate the effect of moment of inertia on a rolling disk. This is a solid disk. It has moment of inertia 1/2 m, the mass, r, the radius, squared. 1/2 mr squared for this solid disk. This is a ring of material. It's hollow in the center. All of its mass is concentrated at the outer radius. The radii of these two are the same, but this one has a moment of inertia of mr squared. So it has a larger moment of inertia, assuming the masses of these two objects are the same. The masses of these two objects, in fact, are not the same. But as it turns out, when you do the calculation, the mass cancels out of the calculation. And what matters is the radius, which is the same, and the distribution of the mass between the center and the outside. So we're going to release both of these from rest at the top of this inclined plane and ask which one of them wins the trip to the bottom. Will it be the one with the larger moment of inertia, mr squared, or the one with the smaller moment of inertia, 1/2 mr squared? So as you can see, the winner is the one with the smaller moment of inertia. Why is that? And the reason is that it has less resistance to turning motion because it has a smaller moment of inertia. So moment of inertia acts a lot like moment of inertia for rotational motion acts a lot like the mass for translational motion. The bigger the mass, the slower it is to start up. The bigger the moment of inertia, the slower it is to start turning.
All right, so you can see with that demo, we can see that D is correct. So the disk win the race. What's in the demo, they talked about this using the idea of rotational inertia is how hard it is to start turning. You can also view this as from the perspective of sort of distributing the same amount of energy. They all have the same kinetic energy because all start from the same potential energy, right? But because of the bigger I for the ring will spend more of its energy to rotation because it's harder to turn, right? And so that it's left over with less kinetic energy to change its position from top to the bottom. Whereas for the hoop for the disk has a smaller I, so smaller energy going into rotating and bigger energy can go into the translational motion, okay? And if there's a bigger energy going to translational motion, there's a bigger center of the mass. So center of the mass for the disk is bigger than the center of the mass for the hoop. So the disk wins, okay? And you can see previously with this example, this is a ball and this one is not rotating at all, right? It's not rotating at all, which means it has no I. All of its energy is used to do the translation. So of course it's going to win. Right? All right. Now I can give you any kind of objects with different shape. I can give you a disc and a ball. You can compare. I can give you a ring and a sphere, and then you can compare. You know which one will win. So whichever has a smaller rotational inertia will win the race. Here is a checkpoint question. It's slightly modified. So instead of rolling down a ramp, they're rolling up a ramp. Okay. So always be careful knowing what do they have in common. So if they're rolling down the ramp, we know that they start out with the same height. They start out with the same potential energy. Now they're rolling up a ramp. But what do they have in common? They have the same velocity. Okay. So the block has a velocity v. That is the center of the mass velocity. And the ball has a center of the mass velocity v as well. Okay, but at the same time, the ball is also rolling. Now let them both go up a ramp. Which one will make it furthest up the ramp? Which one will go highest? So anybody would like to share their thoughts? You have done this checkpoint already, and with the discussion we did previously with the energy approach, how do we use that to look at this question? So which one do you think will make it furthest up the ramp? Would it be the block? If they're raced down the ramp, the block wins. Now, if they're going up a ramp, would also the block would win? In the sense that it's go furthest up? What do you think?
I think it'll be the sphere because it has the rotational inertia. So it'll keep going for further.
So the ball will have the rotational inertia. So other than the 1/2 mv squared, the ball has part of the energy 1/2 I omega squared. So the kinetic energy of the ball is these two parts. The kinetic energy of the block is just this one part. Okay, now be careful. What do they have in common? They have the same mass, okay? The same initial velocity. So this is the same, this is the same. That's very important. If these are the same, then the ball will also has a extra part. So the ball will be moving with more kinetic energy because for whatever reason, it was just giving more energy to begin with. So all of that energy is going to become potential energy at the end, right? So this one will be bigger. So the ball will be going up further, okay? So you can see that you got to be careful of what they give you. Are they starting from the same place? Then you know mgh is the same. The overall kinetic energy is the same. So each of them must have different velocities. Now, if they're starting with the same velocities, then they must have different kinetic energy to begin with, right? All right, any questions about the approach that we just took to answer all of these racing questions? Any questions? Are you good? Okay, when an object is rolling without slipping, okay, there is one extra relationship between the center of the mass velocity and the angular velocity. So previously, we are writing v and omega, right? We treat them as two different objects. But when they're rolling without slipping, these two are actually related. If you know one, you know the other. So how do we find out the relationship between them? So here, this is really a hoop that is doing the rolling without slipping. And if you follow one of the dots, the trajectories is kind of like this, right? It's rolling without slipping. If you follow the one dot on the wheel, you will see this such a trajectory. You can see that, okay, the center of the mass is simply traveling forward, right? The center of mass is not rotating. The center of the mass is simply just moving forward. So you can calculate the center of the mass velocity by looking at the total distance it traveled divided by the total time, distance over time. And you can see that if it is rolling without slipping, right, you can see that the bigger the bicycle wheel, the longer the distance it will cover after you turn it for one round, because that one entire turn is going to be the circumference of the wheel, right? So this distance it moved forward is going to be the circumference of this wheel, of this object, right? We follow this object, you can see that it goes all the way around back to the spot, which means it's traveled all the way around. So going from a one conference, and that's also the distance it traveled forward. So, and this is only, these two are only equal if it's not slipping. You see, if you roll, but you slipped, which means you haven't traveled as much of the distance at your circumference, right? But if it's not slipping, then d is equal to 2 pi r. If it's not slipping, right? So if d is equal to 2 pi r, you can see that if you use 2 pi r divided by t, that is give you omega r, because 2 pi over t is what is omega. Omega is your angular velocity. Angular velocity is describing the change of your position over time. And if you go all the way around, you have go one round, that's 2 pi. That's your radius, right? In the period of t amount of time. So that's omega. So this becomes omega r. So v, the center of the mass, is omega r, which means the kinetic energy is 2 parts 1/2 mv squared plus 1/2 I omega squared. You can replace omega with v, or you can replace v with omega. So omega is v over r. So you can write it like that. Okay. So this is the condition for object rolling without slipping. All right, so finally, we are now ready to use Newton's second law for rotation. We have done a lot of groundwork. We started by defining angular velocity, acceleration. We did that at first, right? We studied how to calculate torque. You recall what is torque? Is R plus F, right? And we discussed angular rotational inertia, I, for different objects and also different axes. We can use parallel axis theorem to calculate I. And now we know all of these quantities. We put them together is torque equals I alpha. Looking at its relationship to Newton's second law, force generate linear acceleration. Torque generate angular acceleration. The bigger the mass, the harder it is to accelerate it. So the bigger the rotational inertia, the harder it is to rotate. So they have very nice sort of one-to-one analogy between these two. Right? So we call this Newton's second law because it is the same thing, but it's just being used for rotation. All right. So now let's look at a question. We have strings and they're wrapped around the circumference of two solid discs, and you pull them with identical forces. Okay. This one has a bigger radius. This is bigger. These two have a smaller radius, but they both have the same moment of inertia, same I. Which disc has a bigger angular acceleration? Okay, so again, we're using torque equals I alpha. Okay, so we're comparing magnitude. I'm not going to add vector signs on it. So torque equals I alpha. We're asking which one has a bigger alpha given this kind of force. So this force, you have to translate back to torque. Okay, which one has a bigger torque? and which one has a smaller moment of inertia, or your alpha is really torque divided by I, right? So you want to compare I1 and I2. All right. Maybe a minute in your discussion group. I think this one should not be too long. I'm gonna go ahead and let you discuss. Minute or minute and a half. Okay? All right, let's go for 10 more seconds. 10 more seconds. Okay, any last minute votes? All right, I'm going to go ahead and close it. Looking at our result, pretty much evenly split between disk 1 or disk 2. One might be tempted to think this one has a bigger moment of inertia because it's bigger, but the problem already told us that they have the same moment of inertia. So probably disk 1 is made of a different material than disk 2, right? So that they end up with the same I, even though one is bigger. So if I1 equals I2, which is given, and if we can know what torque 1 and torque 2 compare, we know how alpha 1 and alpha 2 compare. So torque 1 is simply R1 times F. This is R2 times F because torque is what? R cross F. And R and F right now is perpendicular. They have a 90-degree angle. So this cross product between becomes R times F, right? Sine of 90 degrees is 1. So just RF. Now R1 is longer, is a bigger radius. So torque 1 is bigger than torque 2. So alpha is torque over I. So alpha 1 is torque 1 over I. Will be bigger than alpha 2, which is torque 2 over I, the same I, right? So alpha 1 is bigger than alpha 2. So this one has the biggest angular acceleration, okay? Because you're generating more torque on the same object with the same I. So they're equally hard to rotate, but you give one of them a bigger torque. So it's going to generate a bigger acceleration. So it's disk 1. Okay. All right. So that is very similar to a checkpoint question you have already did. This one, we are looking at the forces acting on two wheels. The two forces, we don't know which one is bigger. That's what we are trying to figure out. What we know about these two hoops or the wheels, they have the same mass. The one has twice the radius of the other. Okay, so this one is bigger. So this one has twice of the radius. Okay, so it's a hoop, so from that I know the rotational inertia is mr squared. So for case 1, I1 is mr squared. Now case 2 is the same mass, right? But twice of the radius. So the bigger one has twice of the radius. So 2r squared is going to be 4mr squared. Okay. Okay, so now we are going to calculate the magnitudes, how the magnitudes of the forces compare. If we are given the angular acceleration is the same, okay, so if alpha is the same, okay, torque is I alpha, but alpha is the same. If we do Newton's second law on case 1, the torque for 1 is F1 times the R cross F. This R is R, right? So that's torque 1 equals I1 alpha 1. I1 is mr squared. Alpha 1. Alpha 1 and alpha 2 are the same, so I'm going to use alpha to represent both. Now let's do case 2. Case 2, torque 2 is I2 alpha. Torque 2 is F2 times a bigger radius, 2r. And angular rotational inertia, the moment of inertia is 4mr squared as we calculated. So the same alpha, if they're the same alpha. So by looking at these, how does F1 and F2 compare? Okay, well, I could get rid of this 2 and make it over here. So F1 times R is mr squared alpha. F2 times R is 2mr squared alpha, right? So F1 is going to be mr alpha. F2 is going to be 2mr alpha. So F2 is twice as much of F1, right? You can see that. Okay, so the answer is B for that checkpoint. You can see that the way we figure this out is by applying Newton's second law for rotation. Torque equals I alpha. If you want to calculate torque, you need to do radius times force. And you want to find I, you need to plug in the rotational inertia equation, and they may have the same I, or in this case, they don't have the same I. Then you have to plug in the mass or whatever radius that they tell you. Okay. So the answer is B. Any questions so far? Are we good? So far, so good? All right. So if we're good, we are going to move forward to a series of 3 questions in a row. Okay. So far, you can look at these 2 problems. What they're doing is they're applying a force and they're generating a torque, but they are rotating about the same fixed stationary axis. They're not moving forward. But the next 3 questions are pulling it while moving further at the same time. So a little bit more complicated. Okay. We may have time to finish all 3, or maybe not. We will take our time with these 2 questions. We'll see how far we go. Okay. So what we have is we have these strings. They're wired around 2 identical pucks. One is wired around toward the center, like in the 2. One is wired around the outer rim, like the 1. And you pull them, pull these parts from rest by using the same force, okay? And they are on a frictionless surface, so there's no friction, no kinetic friction. Okay? So what happens when you pull? You can see that when you start pulling, they're unraveling, right? So they are rolling, they're rolling, and they're also moving from one place to other. So it's similar to the rolling without slipping question, right? So there's translational motion and there's rotational motion as well. So simply just predict which puck do you think will arrive at the finish line first? 1 or 2, or same, or maybe you need more information to determine. Okay, I would say for this particular, the first question, just go ahead and use your intuition. You can simply just do some reasoning using what your intuition that tells you, and later we will be able to sort of parse it out with equations and what to do. But first of all, let's just get intuition what you think it is. And also I will let you go ahead and discuss to see maybe your intuition is the same or different from people in your group. So feel free to just discuss whatever comes to mind. All right, let's go for another 15 seconds. All right, any last minute vote? I'm just looking for intuition here, right? All right, so let's go ahead and end this, and we'll collect some ideas from you guys. So it looks like a majority voted for A, maybe Puck one wins, and less choices for B and C. So I would like to gather for the rest of the time we have. Let's just gather some intuition, different ideas, different reasoning, and we'll keep those ideas and we'll pick it up where we left off next week. So what comes to mind when we are determined that which one arrives at the finish line first? Do you have an intuition, or if you use some reasoning, if you use your Newton's second law, feel free to talk about it. Anybody would like to give us some opinion or different ideas?
The force causes the puck to have both torque and translational motion.
Okay. Yes. Yes. Okay, so that's one idea. Very good. I'm gonna write it down. The force causes torque and translational motion. Okay, that is correct and very good. And any other thoughts? Okay, let's see the chat. Eric asked, there's no rotational motion. I would say there is because you have this thread, right? Once you pull it, it's going to unravel itself. So that would we will consider to be rotation, right? It's like a yo-yo. You can think of this like a yo-yo. There is rotational motion as well as translational motion. So what might be a possible reasoning to support choice A that puck one wins? It generate a bigger torque. Is that right? Okay. Also, there's a chat said less displacement would be referring to less displacement for one or for two. Okay, so for one, it's on the edge, less displacement. Are you talking about the translational displacement from here to here? Okay, all right, so is the idea correct? If you're saying, okay, so that torque generates rotation, one has bigger rotation, so it has less to go into translation. Sounds like that's the reasoning you were talking about, right? So if that's true, I think you would support puck two wins, right? If one has less displacement, then two has more displacement, then puck two will win. So that seems to be supporting puck two wins idea. If that's not correct, please correct me. But that's the idea seems to be what I'm getting. Or maybe someone supports say puck one wins because it has a bigger torque. And puck one will rotate faster, would it? Okay, so I'm just trying to collect a lot of different ideas so that we can use them next time. Anybody have an intuition? Anybody try to, this will be my last question. Anybody try to think about this in your head and imagine, okay, how does this work? And have an intuition between, there's a difference between 1 and 2, or no difference between 1 and 2. Anybody try to think about doing this in your head? Does part 1 have a larger moment of inertia? I would say they are identical. So they're going to have the same I, okay? They have the same moment of inertia. Okay, so that's another fact. I1 equals I2. They're all rotating relative to the center of the mass, so they all have the same moment of inertia. Okay, we are going to just go ahead and stop here for today, and on next Tuesday, we will pick up where we left off and solve all the 3 different questions that I have. Just wanted to give a quick announcement for tomorrow for your, sorry, not tomorrow, on Thursday, that's your midterm 2. It will be available at midnight on Thursday and available until the end of the day on Thursday. You have the same amount of time as you had before, 2 hours, and the similar 20 choices question with the combination of some conceptual multiple choice and some you have to calculate and enter your answer. So exactly similar format as you had for midterm 1. The content will be work and energy, center of the mass, and collisions using conservation of momentum. So those will be covered in midterm 2. Okay, and there's a practice exam and the solutions for the practice exam. So make sure that if you haven't get to that already, you should take a look. Okay, so tomorrow I have office hours from 3 to 4 in the afternoon. Feel free to come and ask questions for your midterm. I do also plan to be opening up my class Zoom, just like what we have today on Thursday, but we won't meet for class. I just want to open it up in case someone had any technical problems they wanted to tell me if I need to reset their exam or something. But I do have a one-time lunch meeting. I usually don't have a lunch meeting on Thursday, but I happen to have that this coming Thursday, so I may be a little bit late to our Zoom, but I will be there eventually. So if you run into any questions, feel free to come in. Okay. All right. So that's all we have for today. Have a good rest of the week. I'll see you guys either on Wednesday if you have questions, or tomorrow during my office hours, or next week. Okay. Bye, everyone.
Thank you, Professor.
Thank you, Professor.
Thanks, everyone.